Hello students. So in previous lectures we have taken some examples from exercise 2.2 of R.R. Goldberg. We'll today continue remaining examples from same exercise. So first example from in today's session is, if Sn is the real sequence such that for any epsilon greater than 0 mod Sn minus L less than epsilon for n greater equal positive integer n naught. Where n naught doesn't depend on epsilon, then show that Sn is equal to L for all but finitely many n's. Means what you have to show, Sn takes L value except few terms of that sequence, or Sn is equal to L for all terms, or Sn is equal to L after n greater equal 1 lakh. Only up to 1 lakh term there may be variation, but there must exist some n naught such that Sn takes same value L after some fixed n naught. After some fixed n naught, that we have to show. On contrary, suppose Sn not equal to L for infinitely many n's. On contrary, suppose Sn is not equal to L for infinitely many n's. Many n's. Then for any positive integer n naught, there exists n greater equal n naught such that mod of Sn minus L is greater than 0, is equal to epsilon greater than 0. Is it clear? So this mod Sn minus L is equal to epsilon n. This is greater than 0. Then this is contradiction to hypothesis. This is contradiction to hypothesis. That is, for any epsilon greater than 0, mod Sn minus L is strictly less than epsilon for any n greater equal n naught, where epsilon doesn't depend on n, n naught. Sorry, n naught doesn't depend on epsilon. So here there exists epsilon n depending on epsilon, Is it clear? And that's why this is contradiction to hypothesis. Therefore, our assumption is wrong. And therefore your Sn must be equal to L. No, wrong. And therefore there exists positive integer n naught such that mod Sn or Sn is equal to L for every n greater equal n naught. Okay. So thus Sn is equal to L for all but finite many n's. Okay, this is equivalent to Sn is equal to L for all but finitely many Sns, many terms. Except few terms, Sn takes L value. Now take next example. If I take say Sn is equal to 10 raised to 7 upon n. Okay, so take example. A par prove that 10 raised to 7 upon n converges to 0 by epsilon n naught definition. By epsilon n naught definition. As n tending to infinity, 1 upon n goes to 0. So 10 raised to 7 into 1 upon n's limit must be 10 raised to 7 into 0. 10 raised to 7 into 0. Is it clear? B part, prove that n upon 10 raised to 7 diverges to infinity. So solution. So here mod of 10 raised to 7 upon n minus 0 is same as 10 raised to 7 upon n is less equal 10 raised to 7 upon n naught for any n greater equal n naught 1. So this is A part solution. Now 10 raised to 7 upon n naught is less than epsilon if and only n naught is greater than 10 raised to 7 upon n naught. Sorry, epsilon. So from 1 and 2, for given epsilon greater than 0, there exists positive integer by Archimedean property. There exists positive integer n naught greater than 10 raised to 7 upon epsilon such that mod of 10 raised to 7 upon n minus 0 is less than epsilon for any n greater equal n naught. And therefore limit n tends to infinity of 10 raised to 7 upon n is 0. B part, what to show that n upon 10 raised to 7 diverges to infinity. Diverges to infinity. Okay. So for m greater than 0, n upon 10 raised to 7 is greater equal n naught upon 10 raised to 7 is greater than m. If and only n naught is greater than m into 10 raised to 7. Thus, for any m greater than 0, there exists positive integer n naught greater than m into 10 raised to 7 such that n upon 10 raised to 7 is greater than m for every n greater equal n naught. And therefore, n upon 10 raised to 7 tends to infinity as n tends to infinity. If somebody asks by epsilon n naught definition, show that n upon 10 raised to 7 has no limit. Okay. So in that, see, it approaches towards infinity. It is divergent sequence. Okay. Suppose C part, by definition, epsilon n naught definition, so that n upon 10 raised to 7 has no limit. On contrary, suppose its limit exists, limit n tends to infinity of n upon 10 raised to 7 is equal to L exists. If I assume this, then what will get? Then For epsilon is equal to 1 greater than 0, there exists positive integer n naught such that mod of n upon 10 raised to 7 minus L is less than 1 for every n greater equal to n naught. This is equivalent to say that L minus 1 is less than n upon 10 raised to 7 is less than L plus 1 for any n greater equal n naught, which implies n is less than 10 raised to 7 into L plus 1 for every n greater equal to n naught, which implies n is bounded above, n is bounded above. Set of natural number. This is contradiction to n is not bounded above. Okay. This is contradiction to n is not bounded above. And therefore our assumption is wrong. What this implies? Which implies limit n tends to infinity of n upon 10 raised to 7 doesn't exist. This is your epsilon n naught definition to verify whether limit of given sequence exists or not. Next example. Let Sn is equal to, say, I'll take, say, 7 raised to n upon 7 factorial, n factorial. So that for every n, so that by definition, prove that limit n tends to infinity of Sn is 0. Sn is 0. So for this, mod of Sn minus 0, which is nothing but mod of 7 raised to n upon n factorial minus 0, is equal to 7 raised to n upon n factorial, which is less equal 7 raised to 7 upon 7 factorial into 7 upon 8, 7 upon 9, and so on, 7 upon n minus 1 into 7 upon n for any n greater than equal to n naught. For any n greater equal n naught. Now if you observe this, each fraction lies between 0 and 1. 7 by 8, 7 by 9, 7 by n minus 1. All of that, these fractions lies between 0 and 1. Therefore, their product also lies between 0 and 1. Okay. So, this here n greater equal 7. 1, which is less equal 7 raised to 7 upon 7 factorial into 7 upon n for any n greater equal 7, since 7 by 8 dot up to 7 upon n minus 1, this product lies between 0 and 1. This is less equal or if I take 7 upon n naught, n greater equal n naught greater than equal to 7. Okay. Now, for epsilon greater than 0, 7 raised to 7 upon 7 factorial into 7 upon n naught is less than epsilon if and only n naught is greater than 7 raised to 7 upon 7 factorial into 7 upon epsilon. Is it clear? So, this is 1, this is 2. From 1 and 2, for given epsilon greater than 0, there exists positive integer n naught greater than maximum of the 7 and 7 raised to 7 upon 7 factorial into 7 upon epsilon such that mod of Sn minus 0 is less than epsilon for any n greater or equal n naught. And therefore, limit n tends to infinity of Sn is 0, where Sn is 7 raised to n upon n factorial. Instead of 7 raised to n upon n factorial, if I take 10 raised to n upon 10 factorial, you have to proceed on same line to prove its limit is 0. While solving the examples, we require one more important result, which is known as sandwich theorem. So we'll discuss one theorem here, sandwich theorem or sandwich principle. Okay, principle. So let Sn or Xn, Yn and Zn are real sequences such that first Xn is less equal Yn less equal Zn for all n. In fact, remember here I am taking for all n, but if this relation is maintained after some fixed n naught, means after 1 lakh term, after 1 crore term, if this relation is maintained, result is true. But for proving, we are assuming it holds for all n. And second, limit of Xn is equal to limit of Zn is L. Then limit of middle sequence, limit n tends to infinity of Yn is also L. Okay. So from 2, for epsilon greater than 0, for given epsilon greater than 0, there exists positive integers say n naught or n1, n2 such that mod of Xn minus L is less than epsilon for every n greater or equal n1, and mod of Zn minus L is less than epsilon for n greater or equal n2. Therefore, for n naught is equal to maximum of n1, n2, mod of Xn minus L and mod of Zn minus L. Both are less than epsilon for any n greater or equal n naught, which implies is L minus epsilon is less than Xn is less than L plus epsilon, and L minus epsilon is less than Zn less than L plus epsilon for any n greater or equal n naught. This is say now 1, 2 and 3. From 1 and 3 now, 1 and 3, this one, L minus epsilon is less than Xn is less equal Yn less equal Zn less than L plus epsilon for any n greater or equal n naught. This implies is L minus epsilon is less than Yn less than L plus epsilon for any n greater or equal n naught. Therefore, mod of Yn minus L less than epsilon for any n greater or equal n naught. And therefore, limit n tends to infinity of Yn must be L. Limit of Yn must be L. Okay. So with this example, today we'll stop here. Thanks for listening this session very patiently. Bye bye.